y'all, welcome to Miss Clarke's chemistry class. This is the second lesson in a series of lessons about nuclear chemistry. We need to talk about how to write out a nuclear decay process. We need to be able to write that equation out. We also need to understand what an alpha particle is. So go get your periodic table, get something to write with, and let's get started. Okay, so let's go through alpha decay. We started with a large nucleus. The reason why a nucleus will go through alpha decay is because a nucleus is too large. So if a nucleus is too large, it might undergo alpha decay. I talked about in a previous lesson what alpha particles are. Now I'm going to show you the process of alpha decay. So first, the nucleus is going to spit out an alpha particle. And remember, an alpha particle is 2 protons and 2 neutrons. If this nucleus spits out 2 protons and 2 neutrons, you know what? I'm going to take a second and I'm going to count these protons. I'm going to call the pink protons. Pink, P, proton, P. And I have got, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I have 12 protons, that means I have magnesium. I'm going to go ahead and count the neutrons real quick. There was 13, so 13 plus 12. This nucleus that I just haphazardly drew, if we wanted to make it a real thing, it'd be magnesium 25. This magnesium has kicked out 2 protons and 2 neutrons. The one thing that you must always remember about any kind of nuclear chemistry, really any kind of chemistry, law of conservation of mass. The reactants has to equal the products. You can't create matter. Same thing here. The atomic number and the mass number are preserved. So if I have 12 protons on the reactant side, I must end with 12 protons on the product side. If the mass number is 25 on the reactant side, the total mass number on the product side also has to be 25. And if you're noticing, I just got rid of 2 protons and 2 neutrons. So if I kick out 2 protons, that means I only have 10 protons. But remember, there's 2 over here. So 10 plus 2 still got that 12. Let me say that again. This nucleus, after it kicks out this alpha particle, which contains 2 protons, if we had 12 protons here, we kick 2 out, we're going to have 10 protons left here. If I have 2 neutrons here, remember I started with 13. I kicked 2 out. Now I'm going to have 11. So we're talking about this nucleus decaying. It doesn't disappear. It doesn't go away. It just changes. It transmutates. That was a word from that first lesson, transmutation. When nuclei undergo radioactive decay, they transmutate. There's a transmutation. The nucleus changes. So this nucleus is going to change from having 12 protons to having 10 protons, from having 13 neutrons to having 11 neutrons. If we want to know what this element turns into, we've got to look at the periodic table and look for number 10. Number 10 is neon. Now, if I want to figure out that mass number, I've got to add my protons and my neutrons, and that gets me 21. Now, I'm going to back up for a second. I drew the alpha particle. Let's actually write its symbol. Alpha particle is a helium nucleus, because if we look at the periodic table at 2 protons, atomic number 2, that's helium. This radioactive nucleus kicks out this alpha particle, and then we just have to figure out what's left over. This is what alpha decay looks like. Let's try an actual problem. We have radium-222, and it is going to go through alpha decay. So first, let's go ahead and kick out that alpha particle. Now we've got to figure out what's left. This first problem, I'm going to work through all of the steps that you need to be thinking. Once we've got that figured out, you do not have to show me all these steps. But for right now, I do want to show you how many protons, how many neutrons, how many protons, neutrons. And then this mystery element, how many protons, how many neutrons. So let's go back to radium. It's 88, so we have 88 protons. Its mass number is 222, so we just need to subtract. Now the helium, the alpha particle, 2 protons, 2 neutrons. So remember, we have to make sure that the proton number is conserved and the neutron number is conserved. So radium started with 88 protons. We kicked out 2 protons. So how many protons is going to be left in this mystery element? So we've got 86. Again, we started with 134 neutrons. We kicked out 2 neutrons. That leaves us with 132 neutrons. So I'm going to go look on the periodic table. I'm going to find number 86, radon. I'm going to go ahead and write that atomic number. Now I need the mass number. So I'm going to add 86 and 132, and I'm getting 218. Okay, so that's when we're counting all the protons and the neutrons. Let's talk about what's happening here. Can we make this easier? Can we make this more streamlined? Is there a shortcut to be had? The atomic number, since we kicked out 2 protons, goes down by 2. You could just subtract 88 minus 2, that's 86. We could do the same thing up top. We started with the mass of 222. Since we lost 2 protons and 2 neutrons, that means we lost 4 particles from the mass. So 222 minus 4, 218. An alpha particle is 2 protons, 2 neutrons. As long as you can keep that straight, you can always figure out that mystery element. And when I say mystery element, it is the resultant isotope of nuclear decay. This nucleus is decaying into this. Let's try another example. But in this example, I'm going to give you the mystery element and the alpha particle, and you just got to tell me what it was. So again, let's remember. Alpha particle is 2 protons and 2 neutrons. So this element here, when it was on the reactant side, it had 2 more protons than it does now. So what that would give us, 95. When we lose 2 protons and 2 neutrons, that's 4 particles from the mass. So this element that we started with is going to have 4 more particles in its mass. And I'm getting 241. So now I'm going to go to the periodic table, figure out what number 95 is. Americium. Working backwards, that wasn't a big deal, right? Let's make sure it all works. 241 minus 4, 237. That looks good. 95 minus 2, 93. So when americium 241 decomposes through alpha decay, we're going to get neptunium 237. Now I would like for you to do this example on your own. Push pause, come back, make sure you got it right. I'll help you set up the isotopic notation for this one first. Okay, so we've got thorium 230. So let's write that in isotopic notation. We've got TH. Remember, 230 is its mass. We always name the isotope by its mass. Let's find TH on the periodic table. That's number 90. Okay, now hit pause and do alpha decay. I'll meet you back in a second. Okay, so I always like to kick the alpha particle out first. That's just, you don't have to if you saw that last example we did. Before I go any further though, I should have said this earlier in the lesson. I typically write alpha particle like this, but we could use Greek letter alpha with the 4 and the 2. Alpha particle is also written like this. That's not the way I was taught. It's not the way I practice, so I always forget about it. But I want to make sure that you know you can use Greek letter alpha with the 4 and the 2. Hopefully you made it this far into the lesson to catch that little tidbit of information. Okay, let's figure out our mystery element. Our 90 is going down by 2, so that's 88. Our 230 is going down by 4, so that's 226. I'm going to look at our periodic table at number 88, radium. So when thorium 230 decomposes through alpha decay, we get that alpha particle, and it decays into radium 226. One last example. Again, this time, I'm also going to ask you to find the reactant, the original isotope. Pause the video. Meet me back in a second. Okay, so if we're working backwards, we're going to know that the atomic number 82, that lead right there, it lost 2 protons. So it originally was 84. And that 210, that represents the loss of 2 neutrons and 2 protons. That's 4. So it was 4 more heavier on the reactant side. And then I'm just going to look for 84 on the periodic table. Polonium. So when polonium 214 undergoes alpha decay, it decays into lead 210 with that alpha particle. Now that alpha particle, it's being spit out of the nucleus. That is radiation. This nuclear chemistry is happening in the nucleus. It spits out this alpha particle, and alpha particle is radiation. Can you believe how easy alpha decay was? Now, there are several other types of radioactive decay that we have to learn how to write the equations for, but they're still pretty simple. So make sure you stay tuned for those upcoming lessons. Until next time, bye y'all.